Hello everyone. Alright, in this video I'm going to teach you about supremum and infimum. But before we get there, we have to learn about upper bounds and lower bounds. So let's learn that. Think about a set. Take a subset of real numbers. We are talking about real numbers. We are in real analysis. If you take a subset of real numbers, this set S, let's call that set S. We say that a real number U is an upper bound for this set if that real number is greater than or equal to every term of that set. Okay, so let's take a simple example. Let's think the set S to be 1, 2 and 3. Okay, you know what, I'm gonna draw it little bit below here. So S set is actually 1, 2 and 3. Now this is a subset of real numbers, a very simple set. Now you want to find a real number that's greater than or equal to every element of this set. What are the choices we have? Well, we know 4 is greater than, definitely greater than 1, 2 and 3, right? 5 is definitely greater than 1, 2 and 3. 1000 is definitely greater than 1, 2 and 3, right? Now how about 3? Well, 3 is also greater than or equal to the elements of this set, right? Now I said the upper bound can be greater than equal to the terms of the set. Okay, so 3 is actually greater than or equal to 1, 2 or 3. Okay, all right, so there are so many upper bounds we can generate here. All of them 3, 4, 5,000, they are upper bounds for this set S. Now what's a lower bound? So lower bound for set S is said to be a real number L, okay, such that this real number L is smaller than or equal to every term of the set, every element of the set. So you, for example, in this set, you want to find a real number that's smaller than 1, 2 and 3. So the choices are, well, 0, right? 0 is a one choice, -1 is a choice, -2 is a choice, right? There are so many choices. So they all are lower bounds. How about 1? Is 1 a lower bound? Yes, smaller than or equal, right? 1 is smaller than or equal to 1, 2 and 3, right? Great. So all these are lower bounds and upper bounds. Now, what's then supremum means? The supremum means the smallest upper bound. When you take all the upper bounds, find the smallest of that, and that's the supremum. So in this case, supremum is 3 for this set. It's the smallest upper bound. Now supremum is like the most accurate upper bound that you can come up with a set. Okay, now of course someone can say, well, for this set S, 1000 is an upper bound. But that's not very accurate, right? Really, 3 is more accurate upper bound. So that's the supremum. We can call it the lowest upper bound. Let's call it LUB. Now what's the infimum? Now infimum is actually the backwards, the largest or the greatest lower bound. GLB, greatest lower bound. So infimum of this set is actually here is 1. That's what supremum and infimum mean. Okay, all right, now we can think about this in another way. Think about a building. Okay, think about a building with so many rooms, and let's say we have a building right here S. Now what's the supremum of this room? We have a room in this building S in the middle. Okay, so what's the supremum of this room? Supremum of this room is going to be the ceiling, what's immediately above it. Okay, and then the infimum, okay, the infimum is going to be the floor of this room, what's immediately below the room. Okay, so that kind of an idea. All right, okay, now someone might think, well, we have this notion or we have this concept called maximum and minimum, and you might ask, well, isn't sup same as maximum and isn't the minimum same as infimum? I mean, what's the maximum of this set S? Of course, maximum of this set is 3. And what's the minimum of this set? Minimum of this set is 1. And they are same to infimum and the supremum, right? But actually, maximum and supremum are two different things. Okay, and it's not the same always, and same with minimum and infimum, they are not the same always. They could be the same but not always. Let me give you an example. Let's think about the set T where all the x values such that x square is less than, strictly less than 2. Okay, all the real numbers, let's put that here, all the real numbers such that x square is less than 2. Now the idea of maximum is that maximum actually has to be a part of the set itself. Maximum has to come from the set. Same with minimum. Minimum has to be a part of the set. But supremum and infimum, they don't need to be the elements of the set. Okay, now think about this. So all the x values such that x square less than 2, well, that's actually x values greater than negative square root 2, and all the x values less than square root 2. So if you draw a real line, okay, so we have square root 2 here, negative square root 2, and square root 2 here, all the real numbers in between negative square root 2 and square root 2. Now what's the supremum? Well, supremum of the set T is going to be square root 2, because all the real numbers that are in between here definitely less than square root 2. And what's the infimum? Infimum of this set is that all the real numbers in this set are definitely larger than negative square root 2, right? That's the infimum. Okay, now here's the question. What's the maximum of this set? So you want to find a real number from this set itself which is larger than all its friends in the set. Is there a real number like that? No, because now square root 2 is no longer a part of this set, okay, because we say strictly less than 2. Okay, so strictly less than square root 2. So square root 2 is not a part of that set. Okay, so there's no maximum. Square root 2 is not the maximum, and there's no maximum. All right, if you want to find a maximum, you have to find it from this region here, right here. And you know, there's real numbers that you can find. You cannot find a real number that's larger than the previous one inside this given set. Okay, same with, you cannot find a minimum. Square root negative square root 2 is not a part, is not a part of this set, is not inside set, because it's strictly, okay, it's strictly x values, the elements of this set are strictly greater than negative square root 2. Negative square root 2 is an infimum but not a minimum. So the idea here is that supremum and infimum, okay, they are any real numbers that fits through the criteria. They doesn't need to be a part of the set, but maximum and minimum, they need to be a part of set. But if supremum is a number from the set, well, then it's same as maximum. Okay, if a set has a maximum and a minimum, then supremum and infimum is going to be same as maximum and minimum. Okay, all right, great. Now let's do some examples from this idea supremum and infimum. All right, so let's try to find the supremum and infimum of this given set T. Now if you look at the elements of this set, they both oscillate between negative and positive numbers. So we have two scenarios. If n is odd, okay, so if n is odd, like if n is equal to 1, if n is equal to 3, what we get is negative 1, and negative 1 over 3 square is 9. Okay, now when n is even, let's see what we get. When n is even, so for example, when n is equal to 2, when n is equal to 4, what do we get? We get 1 over 2 square is 4, 1 over 4 square is, well, 16. So these are some of the elements in this set. Now let's look at the behavior. Let's try to find supremum first. Now if you look at the behavior when n is equal to even, you see that the numbers are getting smaller, right? 1/4, 1/16, next one is going to be what? The next even number is 6, 6 square is 36, so 1 over 36, they are getting smaller and smaller. So the largest number here is 1 over 4, right? On the other hand, if we look at the terms of this sequence, when n is odd, we can see all those terms are negative. So really, clearly, 1 over 4 stands out to be the largest element of this set, right? Okay, so 1 over 4 is actually the supremum. So supremum of this set T is 1 over 4. So supremum actually comes itself from the set. So maximum is also 1 over 4. What I was trying to do here is I wanted to find the supremum from the set itself. Now if I cannot find the supremum by the set itself, I can find a number from outside. I can find any real number that's larger than or equal to larger than any element in this set. Okay, right, let's talk about infimum. Now you want to find a number, infimum of t, which is smaller than every term of this set. Now from -1, when we increase in the odd numbers of n, you can see -1 over 9. So you have -1 here. So you're getting closer to 0, right? I mean, if you forget about negative, the numbers are getting smaller. 1 over 9, next is going to be what? 1 over 25. But so the numerically the value of the terms are getting smaller, but when you include that sign negative, then actually the values of these terms are getting larger, right? You're moving towards 0. So what's the smallest number here? Smallest number here is -1, if you think carefully. Okay, so the infimum itself coming from the set, and infimum is -1. -1 is smaller than every term of this set. So infimum and the minimum is also -1. So that's the supremum and infimum of this set. Alright, so let's look at another example. So we can adapt the idea of supremum and infimum to functions as well. Now think about this function. This function behaves like x when x is strictly less than 1. So it's like a straight line like I have drawn here. Now when x is equal to 1, the function value is not 1. Actually when x is equal to 1, the function value is 0. So that's what we have here. Okay, so there's a discontinuity. Now supremum of this function f is actually, you want to find a real number which is greater than or equal to every function value here. Now if you look at all the function values up to here, all the values are definitely less than 1, right? Okay, x is less than 1 for x strictly less than 1. The function values will be like 0.1, 0.5, right? Numbers like that. And you would expect this function x to be largest when x is equal to 1, but unfortunately when x is equal to 1, the function value is 0. So what's a number that we can bound all these values? The number is 1. The smallest number you can bound all these values is 1. Now notice this function is never equal to 1. Okay, the function is never equal to 1. But remember, supremum doesn't need to be part of the set, or in this case doesn't need to be a function value. It's any real number that you can bound this function, the lowest real number that you can bound this function from above. Now what's the infimum? Now infimum of the function f is, let's have a bracket, otherwise it's like double f. So infimum of this function f is, you want to find a real number that's smaller than, okay, the largest real number that's smaller than all the function values. So it has to be 0, right? If you think about the function value 0, okay, 0 is smaller than all the x values or equal, right? So 0 is the infimum. Now infimum is actually part of the function. That's okay, right? Infimum or supremum can be a part of the function. So supremum of the function is 1, infimum is 0. That's an example from a function. Alright, so before I finish this video, let's do a couple of interesting examples. So here's the first interesting example. Now 1 over n square, the set for n values 1, 2 and 3. So what's the supremum? So you want to find the largest upper bound that can bound g. So supremum of g is going to be what? Let's write it properly. Now if you look at the terms of this set, when n is equal to 1, it's 1, so it's getting smaller, right? 1 over 4, 1 over 9. So they're approaching 0, right? The terms, they're getting to 0. Now what's the smallest number we can bound all these terms of the set? Which has to be 1, right? All the terms here that goes on definitely less than 1, and 1 seems to be like the largest term of the set, which is the maximum of the set, and we can choose it to be the supremum. Now what's the infimum? Infimum of G. Now infimum of G is going to be, as you can see, you want to find a real number that's smaller than or equal to all the terms of this set. Now you can see terms of this set are getting smaller and smaller, and it seems they cannot be negative, so the smallest it can get is 0, right? But it's not going to get 0. It's 0 is not a term of this set, element of this set, okay? But that's the lowest it can get, all right? And 0 is the largest number. You can confidently say that's smaller than every term of this set. So infimum is 0. Now you can see supremum is actually was a part of the set, but infimum was not a part of the set. It's a number, 0 is a real number, but outside from the set. So maximum of the set is also 1, and supremum is also 1. Infimum is 0, but is there a minimum? There's no minimum for this set. Okay, all right. Now let's change this set a little bit. Let's say the set is, let's choose it to be h 1 over x square, such that x is a real number. Now think about this carefully. Real number except 0. Now what's the supremum? Okay, now you might think, well, actually isn't it the same thing? No, it's not the same thing. Here we use non-negative numbers, but here the x values are real numbers other than 0. Important difference, okay? Now if you plot 1 over x square, so if you think about for all the positive x values, the 1 over x square function will look like this. For all the negative x values, the function will look like this, right? They should be same, okay? I'm not the best artist, okay? Right, that's 1 over x square. Now as you can see, when x is getting large, okay, the values of the function is getting small. But what's the largest? Can we find a number larger than any value of this, any value 1 over x square, of 1 over x square? No, right? This function is not bounded above, okay? When x is really small, the function values are getting larger and larger. When x approaching 0, the function values are getting larger and larger, and they are growing without a bound, okay? So really the h is not bounded, okay? Not bounded above, that means it's not bounded, okay? So the supremum in this case, we say supremum of h is infinity, okay? Right, how about the infimum? Now the function is definitely bounded below, right? All the function values 1 over x square is actually greater than 0. So the infimum of h is actually 0. So this is an example where you have an infimum but no supremum. Okay? But the function is still not bounded above, so totally it's not bounded. But it's bounded below, and we have an infimum. So those are some examples of supremum and infimum. So thank you very much for watching this video.